welcome back for the second part of my talk. In the first part, I already showed you some nice pictures of trajectories, motivating these trajectory analysis and motivating why we should be interested in clustering and proximity searching for curves. So let's get right back to the clustering problem. And we've already seen the definition of the Fréchet distance, and I will not repeat this now. Let's look at clustering formulation, a very, let's say, straightforward clustering formulation based on K-center, the K-center problem. So we have a metric, we have a set of elements in the metric space. We want to cluster them, so why not look at the K-center, which basically tells us what is the smallest radius that I can use to cover my data set with balls of radius r, k balls of radius r. Right? And in a very reduced fundamental sense, I set k equals to 1 and I get the minimum closing ball problem. A minimum closing ball problem just asks for one center such that the radius of the ball that I place at this center that still covers my entire data set is minimized. And I'm interested in the continuous version of the problem. So sometimes people also study the discrete version where the center has to come from the input data, but why should we restrict ourselves to this? So here, this is really some element of the metric space. It's not necessarily in my input. That can be the center, and also in the K-center variant. Now, we will see in a minute that this leads to some problems if we formulate the problem like this. And because of this, we're not just interested in any center, but we're interested in simple centers. So because what we want to do for the clustering is we want to summarize our data. So in the end, we will look at these centers of those balls and say, oh, these centers, they kind of describe my data set in a good way. And if I don't constrain the complexity of these centers, then my centers may get very complicated. So what we look at in the first part of this talk is the KL center problem, where my these K polygonal curves, these centers that I'm looking for, they should have at most L vertices. I have two parameters, one parameter for the number of balls and one for the complexity of the centers. Mm-hmm. Why do I look at this problem? Because if we don't restrict ourselves like this, we get an overfitting problem. So let's say my data set is just these two curves, A and B. And I have 1, 2, 3, 4, 5, so 10 vertices that describe my data set. If I look at the exact center, it will have 1, 2, 3, 4, 5, 6, almost the same number of vertices as are in my input there. So it doesn't really give me any summary at all. I can make this a bit more complicated, and I can basically the order of the complexity of the center will be in the order of the complexity of my input data. So this is not very useful because the center really picks up on a lot of noise in the data. So that's why we think it's useful to restrict ourselves to simple centers. But so what's the problem? So what's the complexity of this problem? First of all, this goes back to the unconstrained version where the center can have large complexity. So we can show that the minimum closing ball problem in the metric space is NP hard. This is not true for the Euclidean space, even in high dimensions. But here, just finding this one center is NP hard. And this is, I'm just going to start with this. It's a relatively simple reduction. Even if the curves are in 1D. So these curves are in 1D, and I look at an NP hard problem, the shortest common supersequence problem, over binary alphabet. And let's say I even know what is the value k of the shortest, the length of the shortest common supersequence. And so I'm looking for this common supersequence that contains all of my input sequences. Okay, so I can skip characters on my supersequence, but in this way I should be able to obtain any of the n input sequences. So this problem is NP-hard, and we can reduce it to our minimum closing wall problem using these gadgets here. If I have an input sequence A, B, B, then I replace every character with a gadget that looks like this. If it's an A, I go down. If it's a B, I go up. And in between, I have these extra little zigzags that will allow me to skip over vertices, skip over characters. So the way to think about this is, so if I think of my supersequence, it could be this curve, this a center, a possible center. I will make, so these zigzags, I think of it as only going halfway. This is an A, and then the B goes halfway up. There's another B, there's an A, an A, an A, and I can now find a reparameterization so that these two sequences are within Fréchet distance 1. So here, this whole bunch of curves is just mapped to this one vertex. Then when I go down here, I go down to this A. When I then, this bunch here is mapped to this point. When I go up, I go this. And I can skip any characters in between using, by expanding, by reparameterizing, expanding these shorter zigzags in between. Okay, so I can solve this problem using just finding the center, because now for every input curve I make this transformation, and my center curve will now then in the end I will be able to read off a sequence like this that will be a super sequence. I'm not telling exactly how this works, but I think you can probably figure it out. Okay, now problem is NP-hard, so let's look at approximation algorithm. There is a very simple free approximation algorithm that's based on Gonzalez algorithm. The Gonzalez algorithm just picks a point from the input and then always looks for the point that currently maximizes the radius, picks that as the next center, and so you one after another you pick your centers, and then at every point your radius goes down by a little bit. So here we have those simple centers. We cannot take these centers from our input set, but we can just use simplifications. We used simplifications already in the previous talk. So L simplification is a curve with L vertices that has minimum Fréchet distance to my input curve. So instead of P, I pick the L simplification for P. That's my first center. So some input curve. Then so I collect them in this set C, and then at every point I see where's my radius maximized, what's the input curve that maximizes the objective, the case center objective, and then I take that curve and simplify it and then add it to my set of centers. So this computes a 3 approximation for, so for k equals 1, so it's easy to see by triangle inequality because my simplification, so if there is a center, then the radius of the minimum closing wall will, the radius of the minimum closing wall will be an upper bound on my distance to the simplification, right? Because I could take that radius. So then I can use triangular inequality to get this factor 3. So normally, if I don't have simplification, I get factor 2 approximation, right? So now I get factor 3 approximation. And I can also show this for this Gonzalez algorithm. There is this nice proof that uses a pigeonhole principle. You go one step further, so you look at all of these centers that you picked, 6k, and you go one step further and look at that next one as well. Then you have k plus 1 input curves, and they have to somehow fit into k clusters, and then basically you can show that, so this gives a 3 approximation. The 3 is also tight, I believe, so we had, we showed that this construction, this NP hardness construction, is also a relatively robust approximation. So here in 1D, I think you can get 1.5 approximation would still, or the reduction would still work we go to higher dimensions, we can make a similar construction in the plane and also make it robust to larger approximation factors, almost going up to factor 3. So yeah, so this basically, this is then more or less your KL center problem solved, maybe. There are, of course, many other questions. So in this paper here, we also look at 1 plus epsilon approximation by first looking at a constant factor approximation and then using grids and using signatures to find candidates to get a better approximation factor. But these algorithms, they were exponential in K and L. Okay. And I'm not going to focus on this because what I want to talk about is the sub-trajectory clustering problem. And this now it has a little bit of a different flavor, but I will use, it's still useful to first look at K-center because it will show up here in a slightly different way. So I already alluded to this, and so there was also a question, like what's the length of the trajectory? We usually don't know where these patterns start and end. Here, this is a nice situation. We have these homing pigeons, and they have this. I never know, is it this or this one? I think this is the home. If this is the home they fly to, then some of them get lost. If this is the home they fly to, then they start at different locations. I forgot what exactly the data set is with this. So here there's a clear, at least there's a clear start. And it makes sense to like cluster these. And like the KL center clustering algorithm may like find you a solution like this with these thick lines here describing the centers and kind of nicely describing your data set. But as I said, so sometimes we have this other data sets like this one is a very long, this is one trajectory of a soccer player during one half of a game. So it's very long and it's very, very complicated. So it's, there's a lot of different patterns there. Like you can think of, oh, okay, maybe I want to know like how many times did the player approach the goal or things like that, right? And then you're really interested in sub-trajectories. So so the parameterized curve restricted to a subinterval of the parameterization. And where do you cut these? So we don't know. This is a data set of drifters. They drift in the ocean. And it's a huge data set that has been curated over many years by different countries. And it measures all kinds of properties in the water, like salinity and like pressure, and I don't know, like all kinds of parameters. But also it has the GPS sensor, and it kind of follows the currents of the ocean. And so there are these big streams in the ocean, and maybe you've seen something in the news that like this plastic trash collects always in the same places, and so these are big currents that are more or less static in the ocean. And there are weather events like El Niño, and so that you can also see in these patterns. But it's a lot of trajectory data, and these centers, they just get put there, and then they send their data to a satellite, which is collected, and you don't really know where these currents like start and end. So these are the type of clusters we would be looking for here, where, okay, a lot of these, during different times, maybe different months or so, they kind of follow the same shape. So this is the type of clusters we would be looking for in a sub-trajectory clustering problem, right? And also here, this is the full body motion data. This is the SIMU data set. Like a person is walking and then jumping and then kicking and doing these type of movements. And you should be able to cluster them if you know where to cut these trajectories, right? How do we even find how do we even formulate this as an optimization problem? So this is a good question, and there have been. I think what people usually do in practice is they cut the trajectories at the points where they think this is a good point to cut, and then they apply clustering algorithms. But we were interested in formulating one optimization problem that does both the cutting and the clustering. So where would be the best places to cut so that you get a good clustering? And our approach, and I'm kind of skipping over related work that had different, maybe different formulations of this. I'm just going to focus on this one formulation that I think is, from my view, is a kind of a clean formulation. And it uses set cover. In some way, what we want to use is set cover in this range space of metric balls that we have already looked at before on the Fréchet distance. But so let's first look at this. So I'm sure that most of you will be familiar with the set cover algorithm, but let's set cover problem. But maybe let's go back and review like the basics. We have, you can think of set cover problem as you're given a bipartite graph, and this bipartite graph encodes a set system. On one side you have the ground set, and on the other side you make an edge to every point that is in your set. So every point here represents a set. Every neighborhood here represents a set. And now you can, if you think about it this way, what you're interested in is a small, the smallest possible subset of sets, so that their neighborhood covers all of the ground set. Okay. And thinking about it this way, the problem is also equivalent to hitting set if you take the dual point of view. So if you say, okay, this is my ground set and these are my sets, then so a hitting set, this is the smallest possible selection of the ground set that is contained in all the sets. So a set cover solution is also a hitting set solution in the dual set system, which just means that you switch the roles of the two sets in your bipartite graph. Okay, why is this relevant? Well, it will be relevant if we want to find a discrete problem to solve, because these input trajectories are continuous curves, and potentially there's an infinite number of such trajectories that you may want to look at, because you can cut them at any point. This dual point of view gives us a nice way to discretize. So you can go back to Euclidean K-center problem, and that's if you fix K, you look at the decision problem, that's set cover for I fix K and fix the radius, so decision problem. Then you have all of those balls of radius R, and you want to cover all your input. Okay? So the set cover. It's not a finite set system because you can choose your centers anywhere in the plane. But if I look at the dual, and I look at the arrangement of balls centered at my input, then I get a discrete problem, because in every cell, if I place a center in a cell, no matter where in the cell, it will cover exactly the same subset. So that gives me a discrete set of candidates that they could also cover, that I potentially would have to look at, but not more. How do we now define our subtrajectory clustering problems? This is, I think it probably takes a bit to digest, so let's maybe look at it really carefully. The question is, what are my sets and what is my ground set? So when we started thinking about this, we always got a bit confused, because what is really the ground set? Let's say you have just one long curve, and you want to cluster the subtrajectories of this curve. And it's enough to just think of this one long curve, because it's possible if you can solve this problem, then you can use the same techniques to cluster other, like more, if it's already cut at some places, or if there are more several curves. Okay, so you have one long curve, and there are many subtrajectories that you don't care about. You don't want to cover like all subtrajectories or something like this. That doesn't make any sense. But you can try to cover the curve. So the ground set is the curve, all the points on the curve, and my sets are metric balls that cover part of the curve. And so a set could be, for example, a line segment, defined by a line segment Q. And I look at the metric ball of this line segment, and I look at all the points on the curve that have a curve in that metric ball. So it sounds more complicated than it should be, but I don't know how to say it any simpler. It's essentially what you can think of is also, you can also think of all possible curves in this metric ball, and then union over their points on those subtrajectories, and this will be your set. Yeah, so for example, these two subtrajectories, they are in the set defined by Q, but this one here goes in the wrong direction. So P goes like this, and this one is not in the metric ball because it goes in the wrong direction. Okay, and now the problem we want to, so now I can say, okay, Q I define this coverage function, which gives me all of the, all of the points in my parameter space. So I have the 0, 1 parameterization, right? All of the points so that there exists a curve that is within Fréchet distance delta to Q, and I union over all of them. This is my coverage. You can think of this set as a set of intervals from the 0, 1 interval, a set of subintervals. And it could, depending on how complicated the curve P is, there could be many intervals actually. It could be many disjoint intervals that just are described, that just described as one set defined by Q. And then we want to cover the entire interval 0, 1 using these sets, and we can choose them freely. But again, we have this problem that we need to choose a parameter for the complexity of the centers, because if I don't constrain it, then I could just choose P, and P covers itself. So let's look at the version where we just cluster with line segments. Okay, so it's very kind of constrained, but it's still complicated enough, I think, in terms of what we have to achieve. What I want to do is I want to use a hitting set algorithm that works for set systems of low VC dimension. And why? Because if I don't, I just don't know any better way of doing it. In general, set cover is hard to approximate within approximation factor log n, and I think that's not good enough. I want to be better than this. If I can derive a set system that will give me an approximation to this for this problem that has low VC dimension, then I may be able to achieve a better approximation factor. And in the end, we will get a bi-criteria approximation. So let's look at the VC dimension. What is this? So the VC dimension describes, is like a way to describe complexity of a set system that is it comes from learning theory. It's used in many different applications, and it's defined as follows. So we say a subset of the ground set is shattered by a set system if we can describe any subset of this set S by intersecting with the sets from the set system. And the VC dimension is the largest possible set that can be shattered. Now, for example, if you have the set system, you look at the set system of rectangles in R2, then I can shatter any set of 4 points, but if I have 5 points, I can never shatter it, because there will always be a point that, so for example, here there's a point in the middle, and if I just want to express the subset only consisting of those 4 points, I cannot do it by intersection with a rectangle. And so there will always be, this point could be somewhere on the edge here, but there will always be this kind of this point that you cannot exclude from the set. So you cannot describe every subset. And that proves the VC dimension is at most 4. It cannot be 5, and then you still have to show that you can always shatter 4 points, but I leave that as a simple exercise. And there's a very important theorem, the epsilon net theorem by Hausler and Welzel, that says for any set system of a c dimension delta, any value epsilon, we can obtain a so-called epsilon just by sampling, and the sample is large enough with constant probability. And in epsilon net, you can think of it as a hitting set for the large sets. So an epsilon net is a subset of the ground set that hits all the sets that have volume at least a fraction of epsilon of the entire ground set. So so just by sampling, you almost get an epsilon, and almost get an hitting set when the VC dimension is small. And there's this algorithm by basically it's a multiplicative weights update algorithm or a variant of this that solves the the hitting set problem using basically. Okay, per se, maybe it doesn't have so much to do with epsilon nets, but we can combine the two to get a hitting set algorithm that gives us a log k approximation, where k is the optimal size of the hitting set. And what do we do is, so what we do is the following. So we compute an epsilon net, so we can compute it by sampling. And then we check if there is a set that is not hit. And if it's really an epsilon net, then any set that is not hit must be small. It must have a size fraction of at most epsilon v. So we want to make sure we hit this set. But it's too small to be hit by an epsilon net, to be guaranteed to be hit by an epsilon net. So what we do, we increase the weight of all the points in this set. We double the weight of all the points in this set. And next time we sample these points in there, they will be sampled with double the probability. Yeah? So we have to rescale the entire thing, but it's basically the probability is increased. And so one can show that you only need like an expectation k times log size of the ground set rounds of this algorithm until surely an epsilon net will be a hitting set. Because one way to think about it is that, okay, you fix a solution like an optimal hitting set, and then it hits all the sets. So, and that means the points, they are contained in all the sets. And in every round, I will increase the weight of at least one of these points. So in the end, my hitting set will have, in the end, so the sets that this hitting set is contained in will have, in the end, large weight. So I will have found an epsilon that will be a hitting set in the end. Yeah, so I'm not really doing the math here, but it's basically the thing is when you increase the weights of these small sets, the total weight does not increase too much because the sets are small, and so the weight increases exponentially, but then the total weight does not increase so much. So then, I mean, in the end, it turns out that after log n, k times log n rounds, you will have. We have reached
quick
this.
question. What's R sub t here?
What is
R sub t?
Okay. Yes. So R sub t is the set that the dual set of the point t. Okay. So let's look at the algorithm. So we sample a subset according to the weights, and this will be with constant probability. It will be an epsilon net if. And we'll just work with that set. Then, we can check if it's a hitting set. If it's a hitting set, then we're done. If it's not a hitting set, there must be a point that on the curve that's uncovered. So there must be a set that is not hit, and this set is RT. So. So it's a bit confusing because already the definition of the set system is relatively complicated, but now you have to look at the dual of that, right? Because we are solving the hitting set problem. So let's maybe go back to the slide where we define this. So here a set is defined by this Okay. So the set is defined by Q, and the ground set is just the points on P. So in the dual set system, we will have any point on the curve defines a set, and these are all the centers that would contain this point in their set. What I haven't told you yet is how we kind of relax the problem. We go to an intermediate set system that is easier to handle, and that kind of preserves our solution quality up to certain approximation factors. So it's easier maybe to already think about this, what it looks like. In the end, what we will do is we will only take centers from the curve itself, so sub-trajectories from the curve itself, and it's even sufficient to only look at sub-edges, actually. So for any edge of the curve, I only have to look at an edge contained in that edge. So it's not obvious why this works, but we have a certain type of simplification that we can use to pre-process the curve that will allow us to just look at just only look at these sub-edges, so as candidates. It's called it's like a maximal simplification, and it has the property that basically locally you cannot simplify further, otherwise your error would go up by too much, and then in the end so your centers will, if you just look at line segments, they will, And another thing maybe also to mention here is if I haven't really said what our two criteria for the bicriterion approximation, what the two parameters are. So the one parameter is the radius of the metric ball. So it's a parameter, but then we allow that radius to be slightly larger. So it's a very natural parameter to look at. The other parameter is the number of clusters. So those are the two parameters, and we do approximation in both, so we relax both of them. So for the simplification, obviously with triangle inequality, and so we get this radius that it can be a bit larger, but not too much. And with the number of sets, we can play a lot with that, because if I have a long center that covers part of my curve, I can always split it into, so let's say I have I have a long edge. I can always split it into sub-edges, and my number of sets will only increase by, the complexity of like how many things I split it into. The coverage will stay the same. So so that way we can like reduce the problem to something simpler, so that we only have to look at these sub-edges. So now what does it mean for a point to be covered? So it's so what is this RT? So T is a point not covered, and RT is the set of sub-edges that would have this point in their set. Okay, and now we're still not discrete yet. We still have an infinite set system. So in this variant, we just subsample the curve. So we get points, we place points on the curve evenly spaced, and this will be our ground set. And then we can show that our, so this RT then will be a, so these points then induce kind of critical points where these sets, these subtrajectories start and end, and then so it will be a finite set in the end, and so this will be a finite thing in the end. Right. So I haven't really talked about the VC dimension yet, but so I hope what RT is like somewhat vaguely clear. Right. So if the set is large, then it's not an epsilon net, so our sample was wrong. We had a failure here in the sampling, so we just resample. Yeah. If the size of the set is small, then we do the weight update. And then, so we get the log k approximation from the, let's see, what is the, why does it say log v? I think it's log k. We have log v rounds, but the size only grows by log k somehow. In the end, we return a hitting set that has size k times, what is delta?
VC dimension.
Oh yeah, okay. Delta. Before it was the radius. No, okay. Right. Right. So what now? The question is, what is the VC dimension? Because so k log k. This is log k is an approximation that you get from this algorithm per se. And what's our VC dimension? Well, we can in our reduced kind of problem, we can actually reduce it to unions of rectangles. So there are also other bounds on the VC dimension for these Fréchet metric balls that I'm not talking about here that we can also use, but this is maybe a simpler way to look at it. So the other bounds, they use these predicates that I talked about in my first talk. If you have this finite number of predicates that tell you if you know the answer of these predicates, the truth assignment, from that you can deduce whether the curve is in the metric ball or not, then that already gives you a bound on the VC dimension, because it just depending on the size of the size of the set of predicates. But here we can also do something else. So we look at the basically this. What does the set RT look like? So T is a point not covered, and now I want to know what are the sub-edges of an edge that would cover T. And here I look at a specific configuration where I have these three edges. T is contained in the middle edge of those three consecutive edges of my curve. They go like this. And I have this HE that corresponds to these three consecutive cells in my free space diagram. And I'm basically interested in all the paths that are monotone and lie inside the free space and their maximal extensions in this dimension. So I project them here, and so this sub-edge from alpha 1 to alpha 2, that would cover the point T, because this path covers T. There would be the subcurve here that contains T that's in the metric ball. And so if you look at this picture, I think you probably believe me that the possible starting points and end points of this path on this curve, they form a rectangle, because you have this kind of independence between this and this. So here you can go down like up to this point, and here you can go up to this point, but then you also have this constraint here, so you cannot go below this point here because the path has to be monotone. So this gives you another beta 1 here, and you cannot go above this point here, so alpha cannot start above here because it has to be monotone, it has to cross here. So this rectangle in this configuration kind of describes all possible subedges that would cover T, assuming that I can go backwards on the curve. So this is, you can also, if you find it easier, you can also add a diagonal here and only look at the top half if you only want curves that go forward. But it actually, in the end, doesn't really matter, because we can also draw candidates from the backwards curve. It doesn't really matter. And then it's a rectangle, and rectangles have low VC dimension. And it's a bit more complicated than this, because you're only looking at one edge, and in the end you have these n edges of your curve. So you have these things, but you have these, like a number of those, and also you have a constant number of configurations of how these cells can look like. So you have a union of rectangles actually, but the VC dimension will be constant. And that way we get these results, so at least part of them. So I think what I described is this result. We get a bicriterial approximation, and the radius, the approximation will be constant. In the size of the set cover, you'll have this. So this also works for longer centers, because I can always break a center of L edges into L centers of just one edge each. So that will be approximation for the size, and the running time is near linear in the length, but it also has this parameter lambda, or lambda over delta, where lambda is the length of the curve. So we get this, unfortunately, we also get a dependency on the length of the curve. We also have a purely combinatorial algorithm that doesn't have this, but the dependency on the number of edges n is larger, but still polynomial. And if we can assume that the curve is well behaved, so this is it's C-packed, then we get also better running time. And now, just in the end, to let you, just so you appreciate this result maybe a bit better, I wanted to talk about a lower bound for the VC dimension in a seemingly simple case where the ground set are line segments, and my sets are described by curves. And I want to show you that the VC dimension can be large. So even though this is like the setting that we're looking at, right? We're only covering with these line segments, or our hitting set will have line segments as the ground set. But here I can shatter any set of line segments if my center curves can be complex enough. And the way to show this is I place these lines, so they start on a vertical line here, they end here, and I place them so that each of them has a point on the upper envelope. Okay? Mm-hmm. And now I can select any subset, and I can find a curve that has exactly the subset in its metric ball by just deselecting points by going slightly below this translated envelope to kind of deselect any point from the set. So these line segments, I can translate them by my radius delta, and I get another arrangement here. So this is like my envelope from here, and my curve follows the edges of this arrangement. And in order to have a curve inside its metric ball, it needs to stay on the upper envelope. And so this is by itself, VC dimension does not do the trick, but if we do go to our set system that is kind of a relaxation, a proxy set system, allowing some approximation factors, we can make the VC dimension go down. So this is like the idea here. And this is my last slide. And thank you very much for listening.
Questions?
So, are there any open problems? Any significant open problems? Okay.
So for this problem and also the previous, so I think this is not really satisfactory, but so please go ahead and improve it. So one major open problem, so I missed the open problem session yesterday, but here major open problem is approximation, even constant approximation beyond factor 3. So because all of the lower bounds, so the range reporting lower bounds, they're just for exact, and the conditional lower bounds based on OB, they don't work, as I mentioned, for approximation.
What would you expect? Sublinear?
We don't know anything, so this is, it would be really nice to at least know something. So, so what to expect? It's a good question. So I'm not sure what's known for L infinity. I mean, obviously you have this L infinity embedding into an infinity from the Fréchet distance and also back.
Well, infinity, we know quite surprisingly good things like log D, and basically very efficiently.
Yeah, so what does it, like that plus the embedding, what does it imply? Like the embedding and that, what do they imply? Maybe not L infinity, like
So
go right
actually,
ahead.
the first
like,
results for nearest neighbor search for Fréchet were by embedding into infinity.
But can you avoid these like
I mean, this
exponentials
was
in
for
case?
discrete, not this is continuous results.
Ah,
Even
I
for the
see.
discrete version, you don't know how to get good
Like-
nearest neighbor search with like sub-exponential space.
So the embedding somehow like something is exponential about it, I guess. I'm confused with this.
Embedding is just straight, the m goes to, so you can put, let's say d is equal to 1, and then you put m goes to the dimension or 2 times the dimension, also it's just linear. So
And is the distortion huge or something? Or
it's isometric. I think.
isometric? Oh, it's isometric.
Yeah.
Wait, so where do you lose exponentials?
I mean,
So
the thing is,
we don't like this exponential.
Yeah, that's the thing I would like to.
so
like,
for
not
Fréchet,
happening.
you see, there's like this thing that you have the curve, but also you have the sequence on which you go over the curves. And catching the sequence, I think it's quite hard with embedding. So maybe he has like, I don't remember the Piotr result exactly, but maybe you have like lots of different embeddings and you need to try everything. Maybe something of this speed.
Okay.
It's
And then what's
actually-
this embedding into a product metric where the
I remember,
you
yeah.
only preserve nearest neighbors or something, something like that, like for every traversal, like embed or something like that.
Right. Yeah, because there's also this data structure that if you have near neighbor search, I guess for like a simpler metric, you can get near neighbor search for like a max product of these simple metrics. Some loss, but
Maybe, yeah.
I think you use that for Fréchet, but I don't know what the results are.
But this approximation problem is even open just for computing, approximating the distance itself. So if you have 2 curves and you want to approximate it in sublinear time, then also there we don't, I mean, we
Subquadratic.
only have polynomial approximation factors in sublinear.
Is it sublinear or subquadratic?
Sorry, subquadratic, yes, subquadratic. Okay, what else is
No, but for
open?
CPACT, we know to do subquadratic, right?
Yeah,
Computation,
so if you,
but not nearest neighbor.
yeah.
I see. Or even if you promise that all the curves and queries are CPAC.
Yeah.
I see.
What is CPAC?
So there is this
Something.
notion of compactness that constrains the curve and kind of gets rid of a lot of this zigzag behavior, where I don't think I have any of that.
Is that
there so much.
simplifications that you mentioned?
So what it says is it's like kind of like fatness. So C describes the lengths of the curve inside a ball of radius r. So C, the length of the curve inside a ball of radius r can be at most C times r. So
Okay, so
for any ball of any radius, so if C is a constant, then basically it means you cannot
Yeah.
really stay inside one location too much, and then so that really helps if you combine it with simplification. It really helps in also approximation. For near neighbor searching, we have this covered here. This thing there, we can also show a little bit something for C packets, but not so much. So it helps a little bit, but not so much so far. So what else is open? Yeah, I still have to think about it. I think there are still many questions that are open. Yeah.
Those sound pretty basic.
Okay, thanks.
Other question? Thank you.